Hi everyone. So today we're going to talk about the question of when is a function, a complex function, differentiable. Um, and what we're going to come up with at the end are what are called the Cauchy-Riemann equations, which you're going to grow to love because what they're going to let you do is check when a function's differentiable without going to the definition of a limit. So they're extremely useful and pretty easy to compute. So let's say we have a complex function. And we want to know, is it differentiable? So does f prime of z exist? And let's just recall the definition of the derivative of a complex function. So it's the limit as h approaches 0 of f of z plus h minus f of z. So the change in the output divided by the change in the input as this change goes to 0. And just to remind you, this h is a complex number, and so actually it's going to be convenient to give it a new name. I'm just going to call it delta z. So delta z is just some variable, some complex variable that's approaching 0. And of course, we can break all these variables into their real and imaginary parts. So z is x plus iy. Delta z I'm going to write as its real part is going to be the delta x, and its imaginary part is delta y. Okay. So anyway, this is the expression. One thing we can do is we can think of f. If I think of the complex plane as just its x and y coordinates, its real and imaginary parts separately, I can think of the complex numbers as being identified with R2, with just the plane of pairs of real coordinates. And so I can think of f as a function from just the usual plane R2 to the usual plane R2. So it's thinking of it this way, I want to write it as a function of two variables, basically the real part and the imaginary part, the x and y coordinates, right? And its output is also, it's two coordinates. It's the real part and the imaginary part. So let's call the real part u and call the imaginary part v. And each of those depends on z, and so they each depend on x and y. Okay, and so u and v are functions. I can think of them as real functions with two input variables and one output variable. So they're functions from R2 to R, right? And so these are things that we've seen in like multivariate calculus, for instance. Functions with two real variables as their input and one output, each of them. And so the derivative doesn't really make sense for these kinds of functions because I don't know how to divide by something in R2, so I can't talk about the derivative, but what I can talk about is partial derivatives for these multivariate functions. Oops. So I can define the partial derivatives from multivariate calculus. So for instance, ux, the partial with respect to x, this is just the limit. Basically what I look at is I keep the y value constant and I look at how the x value changes and how that changes the output. And so I look at as delta x goes to 0, u of x plus delta x, I keep y constant. And divide by delta x. And then the partial in the y direction means I keep x constant and I vary y. So this is the limit as delta y goes to 0 of u of x is constant, and then y is varying, divided by delta y. So these are the partial derivatives. And one question you can ask yourself is, how does the complex derivative, which we've defined up here, relate to these partial derivatives of u and also of v? So that's what we want to think about. So what I'm going to do is just write out this limit, the complex limit of f. I'm going to kind of break everything into the real and imaginary parts. Oh, sorry, this should be minus u of xy, should be minus u of xy, right? There we go. Okay. So here's this. And the thing to remember, which we've talked about a lot at this point, is that in order for this derivative to be defined, which means in order for this limit here to exist, it has to be independent of whatever path we choose for delta z to go to 0. Delta z is a complex number, and there's many ways in which it can approach 0. It can approach, along lots of different paths, right? And so this limit exists if it is the same regardless of the path delta z takes as it approaches 0, right? And of course, there's sort of the two most common paths to choose. So let's try comparing what happens when we choose two really simple paths. So let's try first, delta z is real, has no imaginary part. And second, let's try when delta z is purely imaginary. So in the first case, remember delta z is delta x plus delta y. So in the first case, delta y is equal to 0. Sorry, delta z is delta x plus I times delta y. And then if delta z is imaginary, that's saying that delta x equals 0, right? So we're looking at this path first and this path second, right? And let's just see what happens to this limit here as we go along these two different paths, and see what that tells us, the fact that they must be equal. These limits must be equal along these different paths. See what that tells us. Yeah, see what it tells us. So we'll look at one first. Delta z is just going to be purely real, which means delta y is 0. So delta z is just delta x. So in that case, this expression here, let me call it star. So in this case, star is equal to, so delta z is just delta x now. So we're just looking at the limit as delta x goes to 0. And I'm going to write f in terms of its real and imaginary parts. So I have u of, so only the x coordinate is changing. So this is f of z here. or this is f of z plus delta z, actually. Then minus I take this whole thing, divide by delta z, which is just delta x in this case. And so what I can do now is separate this whole expression into its real and imaginary parts. So this is the limit as delta x goes to 0 of, let's see, so u of x plus delta x comma y, that's real, and then minus u of xy, because that's also part of the real part of this expression, over delta x. And what's left is going to be I can pull I out of the limit, so this is I times the limit as delta x goes to 0 of v of x plus delta x, comma y, minus v of xy over delta x. And so you can see that these expressions here, these two limits, these are just partial derivatives in the x direction. And so finally what I get is ux, partial with respect to x, plus I times partial of v with respect to x. Okay, so in conclusion, if I approach, if delta z approaches 0 along the real axis, along the x-axis, then what I get in the limit is just equal to the, basically the partial derivative of f. You can write this as just ddx of f of xy. It's got its real and imaginary part. So if I approach along the x-axis, then what I get involves the partials with respect to x. And a similar thing is going to be true if we look at this second path where delta z is imaginary. So that, in that case, delta z is equal to I times delta y, and delta x equals 0. So what do we get in this case? So the expression looks similar. It's going to be the limit as delta z goes to 0. Delta z is I times delta y, right? And in this case, I'm keeping x constant because delta z is just imaginary. So I can write this as u of x comma y plus, so y is the imaginary part, so it's just y plus delta y, plus iv of x comma y plus delta y, minus u of xy plus iv of xy, and all of this is divided by delta z, which is I times delta y. And again, I'm going to break things up into pieces. So I delta y going to 0, by the way, that's just the same as saying delta y is going to 0. So what are the pieces I want to look at? Well, I'm going to look at the u's and the v's separately. And maybe I'll pull this I out here, actually. So this is equal to 1 over I. I in the denominator, I'll pull that outside the limit. And then here, for the v part, the i's are going to cancel, right? Like this I cancels with that I cancels with that. So there's no more i's there, and so I get the limit delta y goes to 0, v of x y plus delta y minus v of xy divided by, the I already got canceled out there with the i's next to the v's, so just divided by delta y. Okay. So what do we get here? So this part, you can see that that's just the partial of v with respect to y. So this is equal to partial of v with respect to y. And then 1 over I want to simplify that. So 1 over I, remember 1 over a complex number is equal to its conjugate divided by its modulus squared. Conjugate of I is minus I, and then the distance from I to the origin is just 1, so just get minus I here. So that 1 over I is just minus I. So I can write this as Vy of xy plus minus I times, and then this part here is the partial of u with respect to y. So uy of xy. Okay, so this is the expression that we get if we look at the limit, but we have delta z approach the origin along the imaginary axis. Okay, but remember, for the limit to exist, it should be independent of how we approach 0, and so these two expressions should be equal. So f prime of z, let me say it this way, if f prime of z exists, then 1 and 2 must be the same. And so let's see what that says. So 1, we got ux, so the real part was the partial of u with respect to x. The imaginary part was the partial of v with respect to x. So ux plus I times vx. That's 1, that has to equal 2, and 2 was, real part was vy. And then the imaginary part, I'll write it this way, plus I times minus uy of x comma y. Okay, and so these are the Cauchy-Riemann equations. Notice, so these are two complex numbers. If I plug in x and y, the left and right hand side are each complex numbers. And for two complex numbers to be equal, their real and imaginary parts must be equal. So those have to be equal, that's the real part. And maybe I should use different colors. And these have to be equal, because that's the imaginary part of these complex numbers. So what we end up with is a theorem, which we've already proven, that if f of z is differentiable, at some z, I should say at z equals x plus iy, and f of z is u plus iv. It's really two functions, right? It's a real function, it's an imaginary function. Then, let me write this out more carefully. So f of z is u of xy plus I times v of xy. So if it's differentiable, then the following is true, that the partial of u with respect to x at xy has to equal the partial of v with respect to y at xy, and the partial of v with respect to x at xy has to equal the negative of the partial of u with respect to y at xy. And remember, the way we got these equations was by just checking the limit along two different paths. The delta z goes to 0 along the real axis or the imaginary axis. And we get two different expressions. If the limit exists, those expressions have to be equal. And these two equations are coming from looking at just the real and imaginary parts of those expressions. So that's where it comes from. And this is a great way to check whether or not something's not differentiable. Because if it doesn't satisfy these equations, it'll automatically not be differentiable. And that's essentially just saying that those two paths don't agree. A fact, which I'm not going to prove right now. Oh, by the way, I should say these are called the Cauchy-Riemann equations. And as you know, partial derivatives are really easy to compute, and so it's pretty easy to check these. So, and then there's another fact which is kind of even more amazing, which is that if f is a complex function, again, equal to u plus iv, right? Then basically if these partials are defined, so if the partial of u with respect to x and y, the partial of v with respect to x and y are defined and continuous, in an open disk around some point z, then in fact, so anyway, if the partials exist and if they're continuous in some region around a point, then it turns out that satisfying the Cauchy-Riemann equations is enough to prove that the function's differentiable. So then if the Cauchy-Riemann equations are satisfied, f is differentiable. And so what this means for you is that if I ask you if a function, complex function, is differentiable, you no longer have to go to the limit definition of the derivative and check if the limit exists. You have another option available to you, which is just to look at the partial derivatives of the real and imaginary parts and check that they're well behaved, like continuous and stuff, but usually that part's fine. Really just got to check these equations. So the thing that you should do now is look at some examples of functions that we've explored already. So check yourself that, for instance, f of z equals z squared satisfies these equations. And check that some functions that we know aren't differentiable don't satisfy these equations. So like f of z equals conjugate of z, check that it doesn't. And you'll see immediately that actually checking these equations is much easier than trying to prove by hand that these functions are or are not differentiable. All right, that's it for today.